start. So, welcome everybody. It's lovely to see what a wet, cold Melbourne day brings to come to our hearing, to our meetings. And the Friends of Royal Park are joined with the Royal Park Protection Group, Protectors of Public Lands Victoria and Parkville Association in holding one of our special meetings, and we have these several times a year on wider topics in relation to Royal Park. I'm Kay Oddie and I'm Secretary of the Friends of Royal Park, and I'm standing in for our convener Primrose Lenton, who had a prior commitment. I think it was either the opera or concert. Anyway, she's an apology. So, firstly, I'd like to acknowledge the traditional owners of the land that is Royal Park. That's the Wurundjeri Wurrung, and pay respects to their elders past and emerging. And as I've said, today is one of our special meetings that we hold on the wider topics of interest regarding Royal Park. And this is on a very basic aspect of the park, its land, its geology. Our speaker today is Susan White, Dr. Susan White, a geomorphologist, and I'll preempt her more detailed description to say that a geomorphologist studies the relief features of the earth and seeks an interpretation of them based on their origins and development. We're going to hear more. Susan has a long history of interest and study in geography and geomorphology. She first studied and taught geography, including at Flemington High, then graduating to geomorphology in higher degrees at the University of Melbourne, lecturing there and at Victoria University. Her geological interests have spread wider as a consultant and involvement in the Geological Society of Victoria. And I'm sure her Medal of the Order of Australia was for her geological achievements. Susan has a long connection with Royal Park and Parkville as a resident in Manningham Street until the east-west link reared its ugly head with property acquisitions. And she was part of an active Manningham Street community, of which a few members are here today. So please welcome Susan to talk on the geology of Royal Park.
Sent round a whole pile of these cheat sheets, which are the little bookmarks that give the geological timescale, because geological timescale meaning that it's over 4.5 billion years of the Earth's existence. It does people's heads in a bit in terms of talking about hundreds of millions of years and thousands of billions of years and so forth, and then down to last week. So it's really just for your interest, and that it does help when I'm talking about the geological time. So we're talking really here about just really what's Melbourne and this area of Royal Park. So I'm interested in, my main research interests have been in how caves form in relatively young limestones, i.e. less than 65 million years old. So that's quite young, really. That's a couple of months ago, really, in our timescale. But I have a long history of being involved with geological heritage stuff to do with the Geological Society of Australia Victoria Division. And I'll talk a bit about that as well. But we're going to now, is it this way? No, it's this way. Okay. Okay. Right, so, thanks, Ben. So I'm going to talk about some of the locations where there's sites that you can actually go and have a look at in various ways. I'm then going to give you a bit of a short shoot on geological processes and materials and so forth, because sometimes that does people's heads in without, and I'm talking in language that you make some understand. Then we'll talk about the sites and the geological history of Royal Park, geological heritage, which is an area that I'm very interested in, and how you manage geological sites. So now geology, I'll talk about geological heritage, but geology is a big area. It's like saying chemistry, it's huge, and it isn't just rocks and minerals, and it isn't just mining, it includes all of the earth sciences. So geomorphology is a subsection of geology. geology. Now, here you can see here, Royal Park's the largest park in the city of Melbourne, and it's certainly one of the highest points. So you can get really good views, particularly of the landscape, even though it's covered with houses, to the west. Less so to the east because they're just not the same view. But we do get quite a good view across into the newer volcanics area and the different geology over there. And we've got effectively 5 sites that you can see, and you can see some of the aspects of the geology and geomorphology in the broadest sense. And I've got them there. Number 1's Moonee Creek, which is part of the whole landscape. And it has, I've got some things to say about that. The wetlands, which are a constructed, human-made activity, but it does cover some of the old bend of the creek before the Moonee Creek was straightened. Then Royal Park Cutting South Cutting, ML69, and Royal Park Zoo Cutting, the one near the railway station, ML42. I'll explain those numbers in a minute. And an unnamed cutting up on the area where it's just on the bicycle path. Now, if we just now think about some basic principles. Now, the Earth is more or less round. It's not perfectly oval. It's actually slightly pear-shaped. And it's composed of a very thin crust, which is what we're used to. That's, but then you've got everything from solid at the inner core, liquid at the outer core, plastic really in the mantle and the asthenosphere, and then the crust is hard bits. But the hard bits are actually in broken bits. So they're in the plates. We talk about plate tectonics. You've all heard about plate tectonics. Now those plates and subplates, some of them are big plates that then have smaller plates that are part of them. And Australia is on the Australasian plate. Now the Australasian plate goes from the North Island of New Zealand, because the plate boundary actually goes through New Zealand. That's why New Zealand's really very unstable in that sense. It goes, then includes New Guinea, includes some of eastern Indonesia. So that the plate boundary goes through the Celebes and then to the west, and down the west coast, and then to the south. So we're on quite a big plate, a decent sized plate, and we're moving north at about the argument. Are we moving north at 5 centimetres a year or 7 centimetres a year? Big geological argument, this one. Highly entertaining. But it is the fastest moving plate in the world. So we are moving north, and our northern edge is going under the Asian plate in Indonesia. So here's the Asian plate, and we're going under here. It's about, let's say, 5 centimetres a year. But it's important to know that the plate then sits on this semi-plastic area, and these plates go either under, and this is one of the places where these plates join, is one of the places where you get earthquakes. Not the only, but it's certainly a major place. The other thing is geological time, and this is quote which I really like: "We exist by geological consent, subject to change without notice." And we have 2 types of ways in which we count the time. One is relative ages. This is older than this, is older than this, or this is younger than this, in terms of, and if it hasn't been turned over, it's the oldest is on the bottom. It's like the stack of papers on your desk. The things you looked at last were on the bottom. The things you looked at most recently on the top. That principle, until you bioturbated it and it's all turned over. Absolute ages, which are the uranium, thorium, argon, potassium, argon, carbon-14 type dates, are more specific. However, they're not really precise. So carbon-14 only goes back 40,000 years this morning. you know. Whereas uranium lead goes back to the billions of years, because uranium lead gives you the ratio of the isotopes that then mean that you can work out how specifically old it is. However, it's not properly precise. So when I'm talking about 400 million, which I'll be talking about, because that's the oldest rocks you can see in Royal Park, whether it's 410 million or 400 or 398, it doesn't matter, because statistically it's still not particularly it's statistically still valid, because it's still within that sort of general area of that time. As you get closer to present day time, things become more precise. But people often say to you, oh, but geological time, they keep changing it. Well, does it matter if it's last week or today, or does it matter in 400 years, whether you're 400 million years, whether you're a million years different than the date that you were given last week? Doesn't matter. It's not relevant to the argument. It still tells you roughly where it is in the total scheme of things of 4.5 to 5 billion years. So, but I've given you all out of those, and you'll find the numbers don't necessarily match exactly what I might be saying, but they'll be in the same ballpark really. The other thing is we have materials. We have hard materials, rocks and minerals. We have softer materials, which are loose materials like sediments. Now, we have three main types of rocks. Igneous, which are formed from magma, from that magma layer in that section that I just showed you before. If it's volcanic, it's come through to the surface and cooled quickly. It has small crystals because it's cooled quickly. Plutonic, which is like granite, has coarse crystals because it's been intruded in but hasn't come through to the surface, so it's cooled slowly. It's like that old experiment to do with doing crystals on strings that you did in year 8. Probably remember that from year 8. And if it crystallised slowly, the crystal was bigger. If it crystallised quickly, the crystal is smaller. So that's what the main difference is. But the magma, you have basalt, and it's coarse format, but basalt is a volcanic rock. It has small crystals. You struggle to see them, except under a microscope or under a very good magnifying glass. Whereas granite has coarse crystals, and you see them in the eye, and it has a fine-grained version called rhyolite. So we will be talking about basalts today. We haven't got any granites here. Clastic, there's three types. Now, sedimentary, there's three types. They're formed from other fragments of any other rocks, sedimentary, or metamorphic, or igneous, anything. And plastic means it's composed of bits, crunched up bits. Organic means it's formed from organic material like coal and some limestones, gypsum, some of these, and chemical, it's things like limestone. Right? So they're just, and then metamorphic, it's other rocks, including other metamorphic rocks, that have been either heated and or pressured. In other words, they've been squashed or cooked. Okay? And things like marble, which is usually cooked limestone. Squashing it is important for marble, but slate is definitely squashed mudstone rather than cooked. And the other thing is that we talk about plastic sedimentary particles, and they come in different sizes. We all know the difference between clay and sand and granules and boulders, so forth. But sand is a size fraction. It's not a mineral. Not all sand is quartz. Okay. Sand can be made of anything. Boulders can be made of anything. Cobbles can be made of anything. These are size fractions, and these are what go to form sedimentary particles. But I always have to keep saying to people, sand is not a mineral. Sand is a size fraction. Quartz is the mineral. Carbonate, calcium carbonate is the calcite is the mineral. All of these other things are the minerals. The other thing is we have processes and structures. Processes might be marine, shallow or deep water, coastal, emerging or submerging, terrestrial, volcanic, arid, fluvial, in other words rivers, wet, dry, you name it, and tectonic, things like faults and folds of tectonic processes. Now, some processes will operate together. You might get terrestrial things that are volcanic and solutional, or you might get volcanic and glacial. And I'll be at different times today, and I'm talking about different aspects of the Earth's history, but I'll be talking about glacial times and volcanic activity in Royal Park. Now, many processes operate together and separately over time, but you also get this, what I've got that picture of, is a very good example of here we have dipping strata of sediments. You can see we've got faults this way, and it's gone like this, some stage, and then a surface has formed. In other words, this line here is an old Earth surface. It's an old surface like we have now. And then and then there's a time gap there. And then the material on top is unrelated. And we have a couple of those in Royal Park. So that's a really important thing to realise, is that you can have these unconformities which actually indicate there's a time gap and a change sometimes in some of the processes. Now that time gap might be 400 million years, or it might be only 50 million years, or 10 million years. Now the sites. Now we have these sites, I've got this, and we've got the Royal Park South cutting, which many of you will know. It's now a bit covered with vegetation. I'll have a bit to say about vegetation in a minute. I have a bit of a thing about it in terms of geological sites. But we have Many Ponds Creek, which is concreted and straightened, a straightened stream system. It was straightened sometime in late 50s, early 60s, sort of in the time just prior to the extent to the building of the Tullamarine Freeway. It was then concreted because the engineer said this is the way to get rid of floods. Okay, I found it's the way to make floods worse. The wetlands, which were developed after the Commonwealth Games Village development, prior to that it was just various, it was actually a hockey field, I think, and if I remember, and it actually has utilised some of those old stream meanders there. The Royal Park South Gutting, which is the one in the photo here, which I'm going to talk about in some detail. The Royal Park railway station cutting, which you can't get onto now, but you can see the information. If you stand on the other side of the railway line and up on the hill, you can look down and you can see the geology there, but you can't go down. I get very upset if you go down and have a look at it. And there's an number in a circle railway cutting round the bend when the on the cycle trail there. Yeah. So Many Ponds Creek. Now the creek here, you can see here, this is all the creek. Now it's tidal to about here. Right, so actually when the king tides come, the creek really rises there. It's really noticeable. Most of the time there's just this much, but it is mildly saline to here. And some of the creeks in Western Melbourne are saline, have a salt wedge quite a long way up. The Maribyrnong has one up as far as, no, not as far as Jackson's Creek. It's far up as where the the Commonwealth's building, factories were. Up as far as Maribyrnong, it's there. But the creek is tidal here. This creek is tidal to Flemington Road, really. The wetlands occupy some of this meander up there, because before the freeway went in, and before the freeway was developed, when I first did geology at Melbourne Uni in the 60s, you could still see the remnant of the, up here, you could see the remnant of where the creek used to be, where the meander used to be. But that's now obliterated. The creek was originally further east. I'll explain why. It was forced west by the filling of a valley that was further east, which we will then look at when we look at we can see that in that first of the southern railway cutting. You can see where the valley was and the basalt fill in there. And that happened in the Eocene. We better check on the dates from the Eocene. But that's about 40 million years ago. The wetlands are, you have a creek that's here, drainage that's then been a drain that's been draining from the zoo. This part of the creek is semi-natural in the sense that I don't believe it was dug, it was there. It's certainly been there for a long time, but this area here has been modified substantially, particularly this area around here, because you used to be able to get to the underlying Silurian sediments under there, but you can't anymore. It's been sloping stuff down the slope there, on that steep slope there. But the wetlands are now being fed by that creek being drained from the east and by the stormwater system. So, that was really, so we look, I'll just mention something at number 1 and number 2. I'm going to now look at this one here, which is the Southern Railway cutting, number 4 and number 5, which are hard to get any photos of. Now, the Royal Park South Cutting, in my opinion, is a really great site to go and visit, because it's relatively easy to get to. You walk along the bicycle path, not get run over by a bicycle. You can get off the path, and fight your way through the weeds that have grown up in front of the thing. But you have then 2 really clear, different features. So you have this pale grey clay here, and then a unconformity here with a gap in time, and then you have marine sediments here. Now this material here is the weathered older volcanics. Now the older volcanics are a group of volcanic eruptions in more or less eastern Victoria. The most westerly ones are in Bacchus Marsh area, and then they extend really extensively to the east, as far east as Buchan area and Murrindore and far east Gippsland, really. They are predominantly valley flows, where the eruption points have then erupted basalt flow, in other words, what's called a silica pore and generally gas pore flows, very similar to what we see in Hawaii today. And basalt, we think basalt, with our bluestones, are really hard rock, but actually it's not. It weathers very quickly because it doesn't have any free quartz, and quartz is hard to weather. Whereas basalt, which is composed about 90 to 95% feldspars, which is a silicate, in other words, a silica and oxygen combined mineral is much less stable under surface conditions now. So it weathers to clay relatively quickly. Not in 800,000 years like the hard rocks that we see around Melbourne for the newer volcanics, but certainly over 40 million years. It weathers to a clay. And feldspars weather to clay. They weather and they change with moisture and temperature and so forth to clays. So that this is a kaolinergic clay which has formed, and so it's quite soft. When Nick and I lived in Manningham Street for 46 years, and our kids used to go with that end of Royal Park sort of at will, and they used to dig bits of it out, bring home sort of plastic bags of it. But it's quite easy to remove. Actually, is capable of being used for pottery, to clean it up a bit, but it is usable for pottery because it's a kaolite. It's kaolite. But if you look, and I've got a couple more slides of it, you can see that it has filled a valley because it's a valley flow of basalt. It is then, so the bottom surface is not flat, the bottom surface, and the top surface is not particularly flat either. Then have a position where this has filled the valley. Now what happens to the valley then? You've got a filled valley. Instead of it being valley, the water isn't able to there, and the stream is then pushed to the sides. And one of the things is that it was pushed, we don't have any evidence of the water being pushed to the east, but we certainly have evidence that the water was pushed to the west, and that Mooney Ponds Creek then developed, instead of in the valley like this, the valley's full, and then it's cut down beside the harder basalt to start with, because it takes time to erode, and it has eroded down, and the Mooney Ponds Creek is now well down. But it's taken 40 million years to cut down to the level that Mooney Ponds Creek is now. The other thing is that overlying this, at some stage, somewhere you've got marine things. Now that's the sea. Now where the basalt was being, the sea wasn't anywhere near it. It's land. But the gap then that you get between this, 40 million years, and this, which is about, let's say, 15 million years, that's a decent gap. 15 to 10 years. Because the TPR, these are the geological tags that you can put on the rock, is a mid-Miocene sand. So it has a sand size fraction in its sediment. It's a shallow marine deposit. The red bluff sands are quite common across southern Melbourne. Then the type section is at Red Bluff down near Sandringham. And you have these sandy deposits. Sorry, it doesn't look as if it's sandy, it looks as if it's got a lot of iron in it. It probably has got a lot of iron in it because over time, since it's been certainly uplifted and it's not below sea level, it's then had iron seeping through it and so forth. So it's got quite a bit of iron oxides in it, which is why you've got this funny colour. But this is a unconformity or disconformity, but certainly an unconformity with a time gap. There's a time gap of at least 10 to 15 million years. It's quite a decent time gap. There are certainly some of those sediments are not completely flat-lying because shallow marine sediments don't always lie flat. They sometimes you've got low ripples and dunes and so forth, which means that they're not all completely flat. but you've certainly got early Pliocene late Miocene and early Pliocene fossil shells in this area. This used to be this has been dug out a bit by people sampling as fossils. They're not particularly exciting fossils, they're gastropods and bivalves, and most of them are still in existence in terms of the gastropods not so much, but we still have gastropods in Western Port Bay, still living gastropods gastropods is the general word for all the snail-related things. So we have plenty of those. So we've got an this site contains old land surfaces. It contains two different types of sediment, rock deposits. You've got a basalt and a shallow marine. And unconformity and a disconformity at the top. Now at the top you've got a soil formed, but you don't have, the soil's quite thin. Of course, not so much this part of Royal Park, an awful lot of the main hill in Royal Park had most of its soil removed to the MCG, I think. I think the MCG was topped up by soil from the top of Royal Park, so it's been mined. And certainly that soil on the top hill, on the top, this top part of Royal Park was removed.
Susan, what's the time frame between the bottom of the red to the top of it? How many millions of years did that take to deposit? You can't see the top, but
which is the surface, yeah, which is just below the, probably.
You don't have a million of years.
No, it's probably somewhere between 5 and 10 million years. Yeah. I'd have to look that up actually.
Right.
Yeah. You can work it out. But now, this is just another view of it. And again, you can see here that the top of this is not flat. It's curved because most basalt flows are not completely flat. They've got lots of humps in them. Believe me, if you're walking across more recent basalt flows in Western Victoria, you do notice it. But here you can see that these are more or less flat-lying, the ones above. But here's the old surface, and your older basalt, older volcanics fill the valley. Your late tertiary marine sands are the red bluff sandstone fossils, your unconformity, and your present surface with a thin soil. Now that would have been exposed certainly sometime in the Pliocene. We'll talk about that a bit more. The number, and you'll notice that this has a number ML69, and I'll refer these to a bit later, but the Geological Society of Australia Victoria Division documents the geological sites for Victoria, and so we have a system which then is related to the 1 to 250,000 kilometre maps, geological maps of the state, and then each of those are sort of areas, and Melbourne is ML, so the Melbourne sheet is ML. So, but this is a site that was numbered 69. They're just numbered chronologically as you find them, as they're documented, rather than they're not sort of in any specific order except that. The other site along the railway line, the second site along the railway line, is now you don't have any access to. When I was an undergraduate, you could get access. You'd have to organise it with the station master, or it had a small connection. But you can view it from the hill above. Now this is quite different in the sense it still has that unconformity, But the unconformity is quite a different one from the one we saw in the last site, in the sense that these sites here, this is a Silurian mudstone, so that's 400 million years old. Big difference between 40 million and 400 million, order of magnitude difference. And it's a sandstone, mudstone, relatively fine, not particularly coarse sedimentary rock. And it's been folded, so it's been subjected to squashing, pushing, so it's been folded in the same way as if I go like this or like this, it will fold. And we can see quite clearly the folding, and we can see quite clearly the extended bedding planes this way, if you go and have a look. Now it has an angular unconformity because you can see the bedding planes here are not flat lying, but are at an angle to the tertiary red bluff sands. Now the red bluff sands on this top, so it's folded. Then there is a very long period, a really, really long period of exposure. There is a period where there was obviously erosion. There may have been other sediments deposited at different times, but they have been completely removed. They were probably not very thick to start with. I'll talk about that in the next bit. But you can see here the tertiary sands and gravels on top are relatively flat-lying. They are the same tertiary gravels that we saw at the previous site, further south, but there is no basalt here. This was probably more at the top of the hill, and the basalt was coming just down the valleys. The Silurian mudstones do have occasional graptolites, which indicate them, help you give it age, because the particular fossils that you can, long before you had any absolute dating or geological dating up until the 1940s, was done using fossils, because it was relative dating, and this was older than this was older than this. Monograptors are one of the more recent of the graptolites. I'll do that in a minute. But this 400 million years includes Devonian Carboniferous times and all of these periods. So you've got from the Devonian, at least from the Devonian, which is about 380 million years ago, through to about the Miocene, when it's probably most of this area was above land, was above the sea. The dipping mudstones probably were folded during the Devonian, which is a period of major tectonic changes in this part of the world. Lots of things get squashed and cooked at that time, particularly folding. There is some Devonian volcanics in eastern Victoria. The Dandenongs being the closest, but it's volcanics, again it was surface. And there's a lot of Devonian intrusion from the basalt, from the granites, which are beneath the surface, but now have been exposed by erosion. So the angular unconformity represents this very long period of terrestrial conditions. Right, now this unnamed cutting, which is, this was the best thing I could find for it. You can see here that it's pretty much covered with stuff. There is another cutting there, but it's got to be covered with vegetation. But it does have another exposure of the same stratigraphy we're talking about. It's easier to get to if you go on a bike path, but it certainly has some monograptus in some of it as well. This is a photo I got from the internet of the monograptus, and monograptus just has one of these things, because a lot of graptolites have multiple springs. They indicate a deep sea origin, in that they are floaty things. They float, and then their spines, I suppose, for another, or their backbone things, they're sort of a pre-backbone animal, marine animal, and they have the hard parts have sunk into the deep sea sediments. Victoria is one of the great graptolite places of the world. It's one of the places where a lot of graptolite research has been done, and a lot of graptolite understanding of their evolution and what they were and what they are, what they were. They haven't existed since prior to the Permian, so they're well and truly extinct. And the next bit is
Have they actually found graptolites there?
in Well Park. Yes, I found graptolites in the park, monograptus. No, I've lost it. I don't know, I found it years ago. It's now, it used to be able to find the odd one in that area to the west, in that steep slope to the west, but it's now all covered with material that's slid down the side. Now, I'm just going through looking at what has happened to the whole area of, let's say, most of this part of the sort of western Melbourne area, to get some understanding of where the geology of Royal Park fits into the bigger scheme of things. So, between 500 and 440 million years ago, the periods of the Cambrian to the Silurian, you've got deep marine sedimentation. Everything's under the sea here. It's quite deep sea. There's lots of mudstone, siltstones, and then as it becomes shallower, the Silurian sediments are slightly less fine-grained than the slates and shales of the Ordovician. Like the slates and shales of the Castlemaine area indicate that was a deeper sea deposition area than what it was here. By the Silurian, it's all a bit shallower, and so it's sand, it's coarser mudstones and sandstones rather than the really fine slates and shales. In the Silurian, we've got marine deposition of the Dargall Formation. It sometimes changes, they keep changing their names and getting massaged by the sedimentologists. But it's mudstone, sandstones, and they've got graptolites. The graptolites and brachioploids are quite common. By the middle of Devonian, which is then, so that's between Silurian sort of and early Devonians through from 440 to about 410. Remember, we're going backwards. We're coming the other way, so it's 410 million years ago rather than going the other way. But from about 335 million to about 380 is the Middle Devonian. The Middle Devonian in this part of southeastern Australia was a period of a lot of granitic intrusions. Those big granite areas like Hobart, north here, like parts of Wilson's Pond, Mount Buffalo, etc. There's a lot, there are a large number of batholiths which have been intruded into the crust, and they cooled with this blanket of material over them, so they cooled slowly. But they're now being exposed because over that next period, the Carboniferous through onwards, you've got a very long period of exposure. So you've got a long period of weathering, sea level dropped relative to land rose what it was, but most of this area was then. So when it's above sea level, you don't have the same amount of sedimentation. So You have very little sedimentation in the Melbourne area, in the Carboniferous. You've got some sedimentation in the Lake Devonian, you've got some volcanism. You've got not the basalt end of volcanism, you've got the rhyolite volcanism, which is what you see in the Dandenongs. So it's more the fine-grained, like the basalt, like the granite. In the Carboniferous, you've got some faulting and folding. You've got some sedimentation in the Mansfield area, but you don't have any. This area here doesn't appear to have been covered by sea, or if it has, it was pretty shallow and it's all been removed. It could be either. We don't know, and we just have a blank there. In the Permian, Australia was in the high latitudes. It was attached to Antarctica. It's part of Gondwana. We've been attached to all of this period so far. We've been attached to Antarctica. We've been further south, substantially further south, and it's not until a bit later than that that you get the splitting off of Australia from Antarctica. So the last time that this part of Australia, this area here, had ice on it, apart from the occasional decent snowstorm, is the Permian, the early to mid-Permian, and it's a continental ice sheet. The ice moved from south to north, and during the retreat, it left areas of fluvial outwash on the plains. The nearest areas where we see glacial sediments is Bacchus Marsh, where there are quite extensive glacial sediments of Permian age. They are equivalent to the very famous ones at Hallett Cove in South Australia. It's the same ice sheet. But that's the last time we've seen major ice sheets, apart from the small ones in the Pleistocene glaciations during the in Kosciuszko area and Tasmania. Tasmania had more than one glacial period, really proper glacial period, but this part of Australia did not. So we've got these glacial sediments at Bacchus Marsh, and you've got at the end of the Permian is the world's largest extinction event. It removed basically 95% of the biota died. What we've got now is from basically about 5% has developed from the 5% that was left. Now the red bits are the ones that really apply to Royal Park. So in the Triassic, Jurassic and early Cretaceous and early Tertiary, this area was land. It was probably had some minor stream sediments, things like that. We've got bits and pieces, like we have a little bit of Triassic sediments at Bacchus Marsh, with a few really bits of leaf fossils in them. It's the only Triassic sediments in Victoria. There's some Triassic volcanics in far eastern Victoria, but the Council Trench at Bacchus Marsh is the only place where you will see Triassic sediments in Victoria. Australia is still further south, but it's moving north. And it's moving north relatively rapidly. So that by the time of the mid-Miocene, our northern part of Australia has hit the monsoon belt. And so a certain amount of the geology and geomorphology, particularly the geomorphology of northern Australia, relates to the effect of the monsoon, heavy dry situations there. So a lot of the landscape is related to that, although the actual material it's in is really old. It's a really big, an even bigger in unconformity, a lot of time ago. However, by the Eocene, in other words, about 50 to 38 million years ago, you've got the basalt eruptions are occurring. And they've been dated around the 40 million years for most of these. Moonee Ponds Creek was probably diverted to the west and started cutting down, so it's down where it is now. And that's at the edge of the flow in some ways, or it's moved over there. But streams do move, you know, they don't stay in the one place. During the Oligocene, Miocene, you've got rising sea levels. Now, sea level rise and fall is relative to land. So sometimes it's sea level rising faster than land is rising. Sometimes it's land is rising faster than sea. Sometimes they're doing it together at more or less the same time, and sometimes it's the reverse. So the fact that you have a rising sea level doesn't necessarily mean to say it's a rising sea level that we're talking about like now in climate change stuff. Okay? It's not that quick. But it's also to do with the relativity of land and sea. But this part of Australia is still rising faster than the sea levels rise. Whether that continues is not to be sure. But the rising sea levels mean that this area was then below sea level. So either we sunk or the sea level rose, or probably both. Probably a bit of both, and you've got the red bluff sand and the whole range of marine sediments that occur across this area. There's a number of other formations as well as the red bluff sands. Now in Pliocene, which is about 5.5 million years ago to about 3 million years ago, Royal Park area is definitely above the sea level. And Moonee Ponds Creek's still busily cutting down west of the old lava flow, because once it's entrenched in its valley, it will cut down. It might move a bit, but it will cut down. And the newer volcanics start erupting and continue into the Pleistocene. Now the newer volcanics, which is another whole different volcanic event dating from about 6 million years ago through to about 5,000 years ago. So it's a very long event. Mount Cooper near La Trobe University is a volcano, and it has it erupted 6 million years ago. It's one of the earliest ones. But the youngest one is either Mount Gambier or Mount Shank, just over the border in South Australia. So the whole eruption thing youngs to the east. We've also about ageing being a verb, or in geology, younging is a verb as well. Things might young in a particular direction. So that whole, the newer volcanics don't affect this part of, don't affect Royal Park because you're too high for it to get. But around us, we see it. We see it at Mary Creek, we see it at Darabin Creek, we see it in the cuttings along the Eastern Freeway, we see it well and truly once you get over to the west. And you get the Western District lava flow, which extends from Kew to Mount Gambier, is the third largest lava flow in the world. It is very similar to a Hawaiian flow. It's mainly a basalt called Hawaiianite. It's a very similar composition to Hawaii. It would have been very similar to eruptions that we see in Hawaii now. And those of us who have worked on some of the volcanic stuff in this, particularly geomorphology and particularly the volcanic caves, the model for what you see in Hawaii happening now also tells you what might probably happened here in the last 6 million years. In the Pliocene, so It's above the earth, it's above the sea. We do get some Pliocene sediments along the coast, marine sediments along the coast, but not here. We're too far high above sea level. Now the Pleistocene, people think of the Pleistocene in terms of ice ages, 4 ice ages, well there's actually about 15 ice ages. Low sea levels, high cold periods, warmer periods of interglacials. We're in an interglacial now. And the last glacial was in the late Pleistocene. Now, here, it's not glacial in the sense of glaciers and ice. It's cold, dry and windy. Right? We have silts that were easily blown around and deposited. The Duke Gum silts are Pleistocene aged during the last glacial maximum, the LGM, which is between 24 and 17,000 years ago. We're now dealing in thousands of years, not millions of years. It's closer to our time. And we've got gradual glacial. During the Pleistocene, you've got cooling and warming. But you've also got a situation where southeastern Australia is rising. And we know how fast that goes because we have a very well-dated series of dunes between just east of Narracort all the way to the coast, which are coastal dunes. Now, coastal dunes, the base of a coastal dune is within a metre of high sea level. Right? We know that, it's a metre or two. That's near enough in terms of this. Now, the East Narracort dune, which we know has to be older than 800,000 years ago, because it has a reversed polarity after the last time the Earth's magnetic field completely flipped, means that base now is 80 to 83 metres above sea level. So, from sea level now to 100 kilometres inland, it's risen that much. So they have dates for the dunes between the East Narracort dune and the coast. So we've been able to work that out. So the LGM is the last really glacial time. Sea level was about 120 metres lower than it is now relative to the land. Bass Strait didn't exist, it was a swampy area. Port Phillip Bay was a swampy area, and you can see the bathymetry of the stuff that's been done on the bathymetry of Port Phillip Bay. You can see where the creeks and where the Yarra went out and so forth. But we have had gradual, we've seen that we're still moving north and we're still rising. Whether our coastal areas at the moment, they will be subjected to some severe storms and all the problems with severe storms, but whether they'll be flooded by rising sea is more questionable. Not one way or not the other, because we are still rising and we know that when we can measure it. So this is a bit of a cross-section of this, and I've just marked, this is a cross-section across from the northeast to the west, so from the Greensboro area across into western Melbourne, and you can see there the different things, and I've just earmarked where I think Royal Park would have been. So we're quite high up. We can see the older volcanics, and then the older volcanics are covered with, and we've just got this black rock sandstone or red rock sandstone there, that's the same. You can see that the newer volcanics, which are the V's, whereas the older volcanics have upside down V's. And you see you've got a granite intrusion over there towards Greensboro, and you've got the Greensboro plateau, and you've got volcanics on the Greensboro plateau. Now, we'll talk about geological heritage. Now, we go on for 3 weeks of this, but Victoria is the only state or territory in the entire country that doesn't have a state government department dealing with sites of geological or geomorphological significance. The survey was told to get out of that phase in the late 1990s, and they've never gone back to it, although they're very cooperative. It's not their fault. So I'm quite cross about it. So at that time, up until then, GSAV, the Victorian Division, and the survey worked together to run a database, run a system for geological significant sites. And at that time, GSAV took it over. We run a fairly straightforward database. We have over 2,000 sites listed, of which the 2 in Royal Park are listed. And the database is gradually being updated by volunteers, and I'm always looking for volunteers. Now, geological significance, I'll just say a little bit about geology. If you destroy a geological site of real significance, high significance, it's gone forever. You cannot bring it back from somewhere else. You cannot import another version of it there. It's gone. It's mined away. It's removed. So we document sites as either local, international, national, state, regional, local. We have a level by documentation and assessment and comparison. We also document unknown. We sometimes have sites which we haven't worked out what is happening with it yet. And we also document destroyed sites. Now, some destroyed sites tend to be either active quarry faces or destroyed sites where nevertheless there are samples from those sites in let's say, the museum. But you need to know roughly where it came from. Now, we do significance rating, and we periodically reassess them. So, because we may have new information, or the site may have changed its condition, or might have got quarried away, in which case it has to go into destroyed. And sites can be of the full range of geology. It's not just what the narrow idea of what geology is, it is everything. And here's some of the things, and you'll have to put this on the website. Sites, so we have international sites sites that are rare in the world and would probably have a reasonable possibility to be something that's part of a World Heritage thing, but it doesn't mean that they would automatically be World Heritage themselves. They may be part of a larger process. National significance are relatively rare or are important by virtue of their scale. State significance, and see, for example, I'm giving you examples there. Tower Hill's an example of an internationally significant site. Mount Buffalo's a national site. Council Trench Triassic fossil site I was telling you is important for Victoria because it's the only site like that in Victoria. Regional significance, which include the 2 sites in Royal Park, representative regions. Those 2 sites are really good examples of what the geology of Melbourne was like. So that's a good regional site. And local significance, like the Darebin volcanic features, they're all local. Active quarry sites are unknown significance, and destroyed sites. Now, the most interesting destroyed sites happen to be an internationally significant site of the type site for one of the world's oldest plants, Silurian plant at Yale. The council dug it up and spread it across the road. Sites are chosen after recommendation and assessment, and we often consult specialists. I mean, I'm a geomorphologist and I have some other skills as well in geology, but I'm not a paleontologist and I'm not a mineralogist, so I ring up somebody and say, help! And I've just said that. The site ID is based on the names of the 250,000 geological maps. Like the organ pipes is ML16 because it's on the Melbourne sheet. Mildura's MD, for example. Now, some larger and more complex sites have subsites, like the nationally rated Port Campbell site is CL20. But it has 33 subsites that range from local through to international. Because it's a big site, big area, there's lots of small subsites, and this seemed to be the best way of clumping without just giving everything an international or dropping the international off or having it separate or whatever. We've managed to do that. There is an information panel on the Royal Park cutting, South Cutting, which I was involved in dealing with the City Council. You can go and have a look at that. That's quite good. That's the draft of it. It's similar to that. So these are some of the sites I'm talking about. Local significance like Darabin City Council Heritage Study sites with those volcanic sites. They're not rare, they're very common, but they're interesting. We'll go and have a look. They've got some good stuff. The Town Council Trench, that's also on a public reserve. Go and have a look at it. Triassic Park is what's sometimes called. State significance is Mount Koroit Volcanic Cone. Now, that's a really interesting volcano, but it's now, that whole property is now sold for development, so it's having houses built all over it. It's interesting to see what happens to it. That's of state significance. The Potholes Doling Field is a spectacular doling field north of Buchan. And you can see there all of these dolings. Yeah, about 100 of them. A relatively small area. And an international significance is the Coonawarra Cretaceous fish site. That's not very accessible, so but that's probably a good thing because then people can't raid it. Now the other thing is management of sites. Some sites, fine to plant everything on it, but other sites, and it shouldn't be confused with other things. But once you remove an understanding of the geology of an area, you constrain what you know about that area because your understanding is sort of limited just at the top bit because the soil is dependent on your geology. So you need to manage a site so that it contributes to its geological value rather than diminishes it, so that damages it. And where sites have a range of values, you should be based on respecting all of the different sites as well. So it's important to do that. Revegetation can be a problem with some sites. Quarry sites, for example, the vegetation that's taking over the south, the ML49 is probably a pity because you can't see the site properly. It's not doing anything, it's not the material, the plants growing up there are anything more than just environmental weeds. They're not important weeds. And it's a pity that you can't see better. Some sites may have particular vulnerabilities to damage from inappropriate actions, particularly these are mineral and fossil sites, and caves and karst, coastal dunes, cliffs. For example, some coastal dunes, people put marine grass all over it, that stabilises the dune and it wrecks the beach. I think that's with the sand sort of beach. Seen that happen. That can be catastrophic. And information on how to minimise this is available from Geoscience. Okay. I think that's questions. Oops. I think I've got something up. Yeah.
I had a question. You mentioned the major event, the extinction event, and 95%. What kind of life was there that was 95% wiped out?
Well, for example, corals, I'll use corals as an example. There are 3 types of corals. There are 2 that were wiped out, and a third one, which is the one we know now, developed after that. So rugose and tabloid corals are wiped out, but the ones we've got now, I've forgotten what they're called, are a different genera. No, a different phylum. Yeah, so, there's a whole range of things, yes. People often, the reason I made a big fuss about it is that people think that the big extinction event was the one 65 million years ago.
Yeah,
the
sure.
dinosaurs.
Yeah.
But it's not. It certainly it was an important one, but it's one of about 20 extinction events.
But the one that you're talking about wouldn't have had any life forms we would recognize, would it?
Oh yes, it does have a few. Some plants have developed from it, some animals have developed from it. Because, for example, I think amphibia existed prior to it, fish existed prior. So some things, but it's just from a limited pool of them. Yeah. There's a whole lot of things that don't exist. But not all of the phylum collapsed, but some, a substantial proportion of the phylum collapsed.
Thank you for your talk.
Yes. Anyone else? Yeah?
I saw a long time ago that the sign for St Anne's Cathedral was quarried in the Royal Park.
Sorry?
That's true, that's where the quarry is.
Sorry? The quarry? No, I don't know of a quarry in Royal Park. But certainly I do know that the soil from the then topsoil, the MCG, was taken from the top of the hill at Royal Park. So whether that's got morphed into a quarry, I don't know. But that's the only one I know of.
So the MCG was built late 19th century?
Yes. And so late 19th century, they took the soil from the top, probably from this area here,
I think it would have been, or would it have been over the estate net for 40 centuries?
Well, I thought it was at the top here, yeah. But I don't know, I don't look it up. But it certainly came from Royal Park.
Be interesting to know because that history should be around.
Yeah. I mean, it's not secret knowledge. I don't know specifically where it was from.
As part of just changing subject slightly, but as part of the Royal Park Master Plan, they've redone the Cultural Heritage Management Plan, and hopefully, I think we'll see that as part of the process of the consultation. But that, I'm sure, they would have gone back through their surveys to determine where quarries might have been or where they took the topsoil from. I think that's quite
certainly
recent
the topsoil.
history.
Yeah, certainly the topsoil removal is the only one I know of, and there's no evidence of quarries over the other side. There was a huge pile of basalt dumped on the western side between the slope and between what the bicycle paths area, the paths are, and the wetlands. There was a whole lot of that, but that was all dumped. That was all, well, it was when people were digging up bluestone pitches, and that they developed a dump there, which is probably the only reason the skink survived. So, I mean, what you have to really watch is, if you do massive cleanups in some spots, you mightn't really want that because you might be, we're dealing with a landscape that is massively modified by humans anyway. You've got to then think through, are you going to go back to the Pleistocene or are you not? Because you really probably can't.
Susan, where do you think the Moonee Ponds Creek would have gone to the east? Have you got any idea of where it would have been before it got relocated to the basaltic flow?
I suspect the flow was too steep. The flow and the valley, it just didn't cut down. Yeah, or we can't see it. There may be a creek bed at depth there, but we don't, unless you put bores down, and certainly it isn't shown in. The only cutting is the railway cutting. There's no real road cutting on MacArthur Avenue. Yeah, all on that main road going up through the park. There's no cuttings on that. And I suspect, given where the original creek was when Europeans arrived, it looks like it's just on that side. Because in some situations you get cutting down on both sides of the lava flow, and sometimes you only get one, and it just depends on local conditions. For example, how easy it is to cut down.
Yes, that's right. Now, are there any more questions, or?
I'm just saying, when they were doing the east-west link, they did a whole lot of boreholes, of course, going across. I'm not sure, did you ever look at any of those, and did they show anything?
They didn't really show anything. I had a look at them, they didn't show anything.
Keeping them tight for the next time.
But that, I mean, the geology, that was dodgy. I mean, the whole business of putting a cutting connection through what is Royal Park is not very sensible. You'd have to come, or a tunnel through there, you'd have to come up further north. I mean, the geologists were sort of rolling their eyes about that particular one. Yeah.
And
That came out in those hearings, yes. Well, probably, and I think Susan's given a wonderful local, a bigger picture view, but the Royal Park has been, now we can at least go and look at those cuttings and understand them, because you look at the layers and you have no idea. I mean, I think it's very hard to understand, so.
No, I hope everybody's less confused.
And now, if you really are into geology, and you want to look at the whole of Victoria, and Susan won't mind my giving a plug, but Leon Costamans has written The Layman's Guide to Geology, and the photographs in it are fabulous. So if you can get it out of the library, you want to go into a little bit more without getting glazed over in all the terms. He really brings it down to the layperson.
I meant to bring a copy actually.
What's the title?
Landscapes Beneath Our Feet. And
Leon Costamans.
Yeah, and Leon actually, people think of him as a botanist, but he's not. His base degree is geology. Right? He's been a member of the Geological Society since its inception, and he's really quite good geologist. But he also makes it really clear in the introduction to that book. The introduction section is really good at explaining why and how geology is important in general terms. I mean, he's a great communicator, and that is definitely worth having a look at. Yeah.
And as far as Royal Park's concerned, Leon would say, you show me the soil and I'll show you what grows on it. Or the other way around, if you show me what's growing on something, a natural area, I'll tell you what the soil is underneath. So it's all related. Anyways, perhaps we can thank Susan. Sorry, we missed a question.
Thank you. Very quickly, thank you for your talk. I found it very interesting. There were two facts I took out of it, which I'm curious about. One mentioned that this part of the plate is rising.
Yes.
North.
Yeah.
And you said that the leading edge of the plate is also diving under the Asian plate.
Yeah, the leading edge of the plates are diving under Celebes in Indonesia. So the plate, if this is Australia, it's doing that, and then it's sinking around, and Lake Eyre is sinking, and we're coming up. Right? It's doing that. Okay?
It's fluctuating in the process.
Right. So it's like that. People don't realise. I mean, plates. Even though we think plates are rigid, they're only rigid in inverted commas. It's sort of, they do bend and.
Well, thank you. That's my question.
Yeah.